Alright, hello and welcome to a new week. So we're going to finish up these slides really quickly and then start some new ones. The new ones will be extra exciting as well. So I want to show you a really cool example that I sadly don't have a ton of time to explain, but I'm going to give you a ton of code and I have commented it thoroughly. So do look into that if you're interested. But the idea is, let's have a nice little cool dot that's bouncing all over the screen. So like he starts in a random spot maybe, and we know how big the screen is, and it picks a random direction, and it's just going to bounce around and jump off the walls. Okay? So it just bounces around like that. So that is what I would like to show you. And here is how we can program that. Okay? Just keep this in mind. This is what we want. This is not too bad to program, in fact. So we're going to make a class, of course, that keeps track of this bouncing dot and how it moves around. So we better store some things. We better store where the dot is, its coordinates. We should store which direction it's currently going, because maybe we need to change it. Yeah. We'll store that as an offset. Like, okay, go down one and right one, and that will be your next spot dot. Okay? And then we should also like figure out the size of our screen. Maybe it's like 20 by 40. Something like that, because that will tell us like how many spaces to print on each line and when to press enter. Yeah. So that is all you have to store to keep track of this moving dot, and then to actually go and move it, we need some methods. The constructor, its job would be to pick a random spot, because we gotta place the dot somewhere. Oops. We gotta place the dot somewhere, right? So it needs to pick a spot for it. We'll pick a random spot each time. We make a new dot with our constructor, and also a random direction, because we don't want the same program to happen twice. Okay? So that's the constructor, very important. And then I'm going to break down the drawing into two methods, step and draw. So step's going to move the dot. It's going to move the coordinates, alter the direction if it needs to like bounce off a wall or something. If we're over here, we gotta like skip from moving that way to moving this way, and then draw will actually draw the screen. Okay, it will, using the width and height of our screen, print enough spaces and the star in the correct location, and we'll just do that a bunch of times with some pauses in between, and that will be animation. Okay, so here is dot.cpp, and let me show you it running. Okay, it's a long file. Well, don't mind if I do. Let's steal a lot of this from before. .cpp-o dot. Hey. And here is, if I make the screen bigger. There we go. I've also drawn like the coordinates, the edges of the screen as well. So here's our little dot, and it's bouncing around. And it's picking a different spot every time it starts in a different direction, and it's just moving, using all of those functions and fields that we talked about. Okay, so I'm going to stop it with Control-C, and let's rerun it, and you see how it started in a new spot. See how it started in a new spot, and this time it's only going up and down, it seems. Okay, so this is doable with your current knowledge. It's just a little bit of code that we have to get through. So I don't have enough time to go through all of it, I'm sorry, but here's the class with all the fields, the x and y coordinate of the dot, its direction, the screen size x and y, and here is the constructor, the step function, and the draw method. Okay, and I have included a ton of comments, and I really encourage you to read them. This is a really good example of a lot of things at once. Okay, I think probably the best place to study this code is from the main function, because here we like initialize our random number generator, make a new dot, a new bouncing dot object, call it B, with a screen size of 40 and 20, and then repeatedly we do the following until the user presses Control-C and stops us. We're going to draw our current dot, step it a little bit to move it in its current direction, potentially bouncing off a wall, and then we'll pause for a little bit, and that's the pause function from the very beginning of class where I showed you the karaoke example. This is just stopping the program for a little bit so that we can draw every so often, every 0.1 second, and that makes it all animated and nice. Okay, so I do encourage you to look through this code. It's really, really interesting, I think, about how to, like, using the screen size, pick a random spot for the dot, pick a random direction for the dot, and like move it around in its current direction, but like bounce it off a wall if we accidentally went past a wall, and then like drawing the actual screen with the edges with pluses and little pipe characters and dashes. It's all very cool. But this is something that I would like you to study yourself if you're interested. Okay? It's an extended example, and it would be very, very good for you to study this before like a test or something. This is a nice little example of a lot of things. Okay, so that is dot.cpp. That's unfortunately all the time we have for dot. I want you to try it yourself, get it running, and try and figure out why. And I'd be happy to answer any questions that you have about it, of course. Okay, so that's my dot. And if you would like some challenges, I encourage you to try these exercises. So maybe pick an animal that you really like and turn it into a class. Like if you had a cat class, what kind of information fields should you store in a cat class? Like what operations can a cat perform? Meow, eat, things like that, sleep, scratch. That's wonderful. So that's one example. And another nice thing, especially to prepare for your next lab, would be to take a lab /Xilab and re-implement it using classes. Okay? That's exactly what you're doing with the rational numbers. You're re-implementing that using classes, and it's good to get a lot of practice with that because classes are the place to be these days. Everybody loves object-oriented programming and using classes and methods and fields and things. Okay? So those are my exercises for you. And that is all I have to say about objects and classes for now. Maybe we'll come back to these and talk about more later. But now it's time for pointers and memory. I know, it's really, really exciting. This is a really important topic, okay? Unfortunately, it's a very difficult topic. Okay, so do pay attention a little bit more than you normally do for this because historically it's a topic that a lot of people have trouble with when they're first learning. Okay, so pointers and memory, and this is a nice little PDF document that you could read if you're interested. It has a bunch of extra information. It's essentially everything that I'm talking about, maybe summarized in a different way. So if you're having any trouble with your with these slides or your Xi book and it's just not making enough sense, do look at this too. Okay, so without any further ado, let's get started. So I have a fun comic for you. Why in the world would you want to learn pointers? Well, first of all, they have to do with the memory of our system. Okay, how things are going on deep down, how our computer is moving information around. It's a very, very important thing to know because if we can't understand that, then we don't really understand how our programs are executing and how to make them faster or better or more correct. Okay. Also, you learn pointers so that you can laugh at funny jokes like this. Okay, so I'll get you laughing at this by the end of the lecture, I hope. Okay, so, or at least the end of the slides. So I want to show you what memory looks like, first of all. And we say memory a lot. I also say RAM. RAM is another thing that you will have heard of before. Maybe it's something that you're more familiar with if you've like built a PC or something. Memory and RAM are the same thing. They're synonyms. Okay? It's just where information gets stored inside of your program. Okay? So I have words for you now. Let's read the words. Okay. So your computer's memory is just a giant table. Okay? It maps addresses, which are usually large numbers, taking up 64 bits, to bytes, which are 8-bit numbers. Okay? So this is your memory. It looks like this. It has 2 columns. It's got the address column and it's got the value column. All right, and this is all your memory is. At address 0, you can store 8 bits. That's all you can put there. So you can store from 0 to 255. All right, so maybe you're going to put the value 42 at address 0 in your memory, and then at address 1, you can put another 8 bits. Okay, and you can put, I don't know, 43. And maybe at address 2, you can put 87. And at address 3, you can put 255. That's the largest 8-bit number you can store. and then on and on and on forever and ever and ever. For as much RAM as you have that many addresses. Okay, so that's the idea. Every address tells you what's stored there. It's just a big lookup table. It's like, okay, my program stored something in address 2. Let's go look up the value there and use it. Okay, let's print out 87 now. I guess that's where my variable was stored. That's the idea. Okay, so the address is the place. Obviously, that's the metaphor, right? It's like a little mailbox. It's where the value gets stored. It's where a certain byte lives. Okay, so think of it like a house. Think of it like a mailbox. And you can put data there. You can send data to an address, or you can look up the data that's there. So maybe you can look it up and change it. It's like, go to address 2, please, and increment it to 88 now. You can do that. You can store the things, okay, as well as retrieve the things. So that is the idea. Everything you store, every variable, every global variable, every function even, every piece of data in your program has an address associated with it where it lives, okay, and where it can be accessed, where it begins, okay. The concept of begins is very important, so I'm going to add that and put it in italics. Okay, that is all memory is. It's just a big table, so don't be too afraid. All right, so the first question that you might be asking is, well, we know that ints are 4 bytes. How, you just told me you can only store 1 byte at a time. What do you do with an int? How do you store that in memory? How do you do it? So if every address holds just one byte, that's a bit confusing. Let's change that. If every address just holds 1 byte, how in the world do you store an int? And, well, here's the answer. Here's higher memory. Here is other memory. Boop. It's just a big long table. The idea is, if you have, I don't know, 16, 17, 18, 19, if you have memory, you can fill it. You don't have to use these bytes as like solid lines. You can use them as dotted lines. So an integer, if you want to go and store an integer in your program, all it's going to do is take up 4 contiguous bytes. Okay, it's going to be referenced by the starting address. So this is where your int lives. So maybe you had like int x. Oops, getting ahead of myself. Int x equals 42. This is where x lives, okay? X lives at address 16. This is where the int x starts, and we just put 42 in here somehow, okay? We use up all 4 bytes, okay? That's all we do. We treat them as just one bigger box that holds everything. That's all. So hopefully that makes sense, and that's all. You just steal 4 contiguous bytes of addresses, and then you store your int there, and we say that the int is stored at address 16 because that's where it begins, and it takes up all 4 bytes. So it takes up 16, 17, 18, and 19. Okay, so that's all. So that's numbers, ints. What about non-numbers? Remember that everything at the end of the day in your computer is just a bunch of 1s and 0s, okay? Doubles, for example, like how do you store the decimal place? That doesn't make sense. They just take up 8 bytes, and they really are 1s and 0s. The decimal place is encoded in a very weird way, but maybe your book talks about it. I'd be happy to tell you about it in office hours. And then strings are, again, made up of chars, and chars are just ASCII valued bytes, right? And they're just 1 byte at a time, looked up in the ASCII table. So like, I don't know, the space character is number 20 or something, right? That's the idea. Okay, so that's all. Everything is 1s and 0s. It takes up a certain number of contiguous bytes, and that's how you store everything in your program. Everything. Even the code. It's weird, I know. So yeah, let's keep going. I'm going to show you how people like to talk about like raw bytes being stored in places, because it's a whole lot of work to say 1 0 1 1 0 1 1 0. That's the number that's being stored. That's the binary number that's being stored. We don't like doing that. So instead, C++ even and programmers themselves like to use addresses or print addresses in what's called hexadecimal. Okay, it's hex for short, and it's not base 2, it's base 16, so base 2 to the power of 4. And you can remember that because hex, or hexa, in Greek is 6, and then deci is 10, right? So 10 and 6, 16. Okay, and because it's base 16, you have 16 digits to use before you have to like carry a number. And so that means we need more than just 9 digits, which is weird to think about. And so the number after 9, the number that represents 10 in base 16, is the letter A. Okay? A is 10, B is 11, C is 12. It's so odd. 10, 11, 12, 13, 14, 15. 15 in decimal is F in base 16. Isn't that weird? And so that means 16 in decimal is 1 0 in base 16. It's smaller in a sense, which is weird to think about, but it's quite nice. So you can count up to 15 before you need another digit, and oops, that is the idea. So people like writing these numbers because it makes it very easy to write bytes. Any byte is just 2 hex digits. It's very wonderful. Okay. We like to write them in a special way in C++. You can give it a hexadecimal number by saying 0x in front of the number, and that informs C++ that the next thing that I'm about to write is a hexadecimal number. Okay, so that is in code shorthand for 3a base 16. Yeah. And what is this in decimal, you might be asking? Well, it's going to be, just remember, a times 16 to the 0 plus 3 times 16 to the 1. And remember that a is really 10, right? So it's going to be, let's see here, 16 times 3 plus 10, which I don't remember off the top of my head, but guess who does? Python. 3 times 16 plus 10. It's apparently 58. And programming languages are fine with you using this as well, 3a. Yeah, that's 58. It converts it for you. All right, 58. I don't know why I just wrote a 6, sorry. 58 base 10. So that is hexadecimal. That's all you really need to know. It's base 16. Just remember that. Okay, so now let's do some stuff. Let me show you some things. These 3 lines, as innocuous as they might seem, they're doing important stuff to our memory. Okay, they make the boxes. They we used to think about them like this, right? I would draw X, it holds 42, then Y holds 43, and Z holds the value of Y, which is going to be 43 again. So first of all, these are all separate boxes. Z is not the same as Y, it just holds the same value. They could change. And they all have different memory addresses, okay? Which is wonderful. And actually, these 2 lines are equivalent things. So deep down, here's what's really happening. These all have addresses. So maybe X lived at address 0, Y lived at address 4, Z lived at address 8. They didn't have to, but maybe they were all right next to each other, and here's what they would look like in memory. So you got your adder, you got your val, and here's our table. So 0, 1, 2, and 3 get taken up by X. X starts at address 0, and it holds the value 42, however it does. And then 4, 5, 6, 7, 8, 9, 10, 11. So starting at address 0, we have an X. Starting at address 4, we have a Y. Starting at address 8, we have a Z. And 4 through 7 is taken up by Y, which holds 43. And 8 through 11 is taken up by Z, who holds also 43 for now. So yeah, that is the idea. These are all separate places, which means they all have different memory addresses. These are very important things to keep in mind. And this is where we get to make the discovery that, well, variable names, those are just secretly addresses. They're all getting translated to an address. C++ comes up with an address for us, but they're what we use as humans to like think about things, think about where things are placed. They're just our form of addresses. Computers are using numbers, numerical addresses. That's all. Isn't that fun? So yeah, it's really not too bad. It's just every new piece of data has a different like location, and we have to think about that now. Okay, that's important. So here is a question for you that I want you to try. Pause the video, think about it. So let's pretend it's your birthday. Happy birthday. And see if you can figure out what kind of output you get by running this program. What gets printed, okay? So int main, it makes an age variable, it prints out age, and then it calls birthday with age, and it prints out age again, and then it's over. What happens? What gets printed? Please tell me. Okay. Assuming you gave it your best try, let's do it in our minds. So it's making this age variable, and well, it's definitely going to print 19, right? So it's going to print 19, and then it's going to call birthday of age, and well, it should print 20, right? Right. Dun dun dun. Boop. Boop. How about that? Oh no. This is looking weird. Oh no, yeah, some weird things happened here, sorry. When I added this from, I guess, PowerPoint, it put weird non-ASCII characters in my program. Sorry about that. Now I think it's happy. Let's run this program now. Boop. Dun dun dun, birthday. $19.19? What? What's going on here? So that's the answer. The answer is A. Did you get that? Why is it not incrementing age? What? So to understand this, we have to look at the call stack, and I have used this giant emoji to talk about this. Okay, so birthday and main are what's getting called. Main gets called first, and then birthday gets called right after that. And this is what the stack looks like, but that's not the full story. So let's zoom in. Isn't that fun? And so this is what the stack really looks like. It's got age, which is initially set to 19. Okay? Age holds 19, and then remember this has an address now. We can think about it this way. It lives at address 100 maybe, main's age. And then it's calling this function birthday, and it's getting passed an argument in for its a parameter. So a is going to be set to, in this case, age when we call birthday. And so it's going to put whatever age is, which is 19, into a. And so a holds 19. And remember, these are two separate places in memory. They're not the same, as evidenced by this different address. That's useful. Okay. So now I think you can see what's going wrong. A gets incremented, yeah. But that does nothing to this age down here. It was a separate box in memory. You see that? That was the problem, and I hope you see it now, if you didn't before. So we know how to fix this, right? We've learned about references, and that's one way to fix this. But actually, deep down, references are secretly using something called pointers, okay? And so that's why we're about to talk about it. So we want to learn exactly how C++ is doing this. How is our code really getting executed? Down at the lowest level, at the level of memory and addresses and value mappings. Okay? You're now ready to know everything. Are you ready? Let's do this. So here is what it means to be a pointer. Okay? It is, it's a lot of information, I know, but it is good to know. It's very, very important to know how our programs are getting run. So here's the idea. A pointer, it's just another kind of variable. It is a new type, in a sense. Okay? A pointer is just a variable, and what it does is it holds the address of another variable. That's the key. That's all it does. Okay? Maybe I should put that in bold too. Okay? And the reason it's called a pointer is because we say that the pointer points to that variable. Like, it holds its address, it's got it in its phone book, and so it can immediately call it or go to that place. Like, it can tell its version of low-level computer Google Maps, hey, I want to go here, I want to put a value here. Okay? And here's how you do it. Here's how you make a pointer. It's just a variable that holds the address of another variable. Here's how you do it. This is how you declare it. You say the type that you want to point to, like if you have an int variable that you want to hold the address of, you'd put int here. Okay? And then you put a star. That's all that's new, is this star. That's the one addition. That's all you have to worry about, is putting the star, and then you give it a name, just like another variable. Give it whatever name you want. It could be like P or something. And the white space around this star, just like for references, remember the ampersand, you can put it wherever you want. You can put it next to the type, you can put it next to the name, or you can put it in the middle like this. It doesn't really matter. Pointers, though, remember, they're type specific. So this type part is very, very important. Okay? So here is how you do it. You can say int star p, semicolon. And so this is just a variable. It is, well, it's a box in memory, right? It's called p. It itself has its own address, like maybe it's address 100, and right now it's holding junk. It's holding a random address. It's holding a junk address because that's what pointers hold. They hold addresses of other things. Okay? If you don't like that it holds a junk address, but you don't have something normal for it yet, you don't have a real address yet, you can use the special variable called null pointer. Okay? This is a special address that's not used, and it's the 0 value. 0 is really an address that is never used by your program. Okay? So you can put 0 inside of there, and that's what null pointer is. It'll make it 0. Okay? And 0 is an address that you do not have access to. Nobody ever does. Okay? Things don't really live there. So yeah, that is int star p, and you can set it to be null pointer. There you go. Okay, that's how you declare a pointer. That's all you have to do. Now let's talk about how we can use them, because really we want to use a pointer p, to point to another integer. You see that? You kind of read it backwards. So let's have it hold the address of this variable x. Okay? Here we go. We're going to make an int and a pointer to that int. So let's remember what's happening in memory now. We're going to say int x equals 5. That makes this box. Apparently x is living at address 100, or 100, hexadecimal, not actually 100, right? And then we can declare int star p, but right now it's holding a garbage address. We want to give it the address of x. We want to put 100 in here. That's what we want. How do we do that? Okay? And this is where I apologize profusely, because C++ sucks. For this reason and a couple others. They reuse the ampersand. I'm so sorry. The ampersand on the right side of an equality, on the right side of an assignment statement, without being used as part of a type, is called the address of operator. So it goes and gets the address of the variable that you type next. Okay? So this translates to the address of x. So read it like that. Address of x. Okay, that's what I want you to read that as. And this sets p to hold the address of x, which is 100, and so it puts 100 in this box. It goes to x. It's like, okay, where do you live, x? What's your address? And it puts it there. And now, the whole reason we call this pointers is because this kind of action is going on, this graphical thing. P is pointing to x. There's like an arrow. It knows how to get there. That's the key. Okay? Are you ready? So, now, let me show you this. Boop, boop, boop. Once you have this set up, you can use another operator called star. So again, sorry, C++ sucks. The operator star, usually, the way I just taught it to you, it means pointer to. If you put it next to a type, it's like, okay, it's a pointer to an int. Okay, that makes sense. And now if you want to use the pointer and go to the place where the address lies, like go to the box in memory at address 100 that this pointer is pointing to, follow the pointer, that's the idea, you can use star again, sorry, without putting it next to your type. And this is called the dereference operator. So this dereferences p. You can read it like that. Dereference p. And what it does is it follows the pointer to the right of it. Okay? And it goes along the arrow in a sense. So with that in mind, can you tell me what this will print? If I have all this code set up from before, this and this, and also this, and then I print cout star p with this memory going on. What do you think? And the answer is going to be 5, because this was what it means. It dereference follows the pointer and gets the value there. Okay, it's like, okay, go to this location and show me the value, please. That's what it's doing. So now let's do some code. Pointers.cpp, so int x equals 42, int star p equals the address of x. Okay, p holds the address of, we say, x. Okay, that's the idea. And now, cout star p follows p to get the value at the address it's pointing to, which is a long-winded way of saying it follows the pointer and goes to the box that it's pointing to and gets the thing inside. Boop. Boop. 42. Let me show you how it prints pointers. The address of x is like that, and this is the address. It's like where it lives in memory, wherever x lives in memory. Are you ready? Oops. This is the hexadecimal, 0x, yeah? This is the address of x, apparently, for this run of the program. It changes when you run the program a different time. It gets put in a different spot, because your program gets put wherever in memory there's free space. Okay? So you can run this a bunch of different times, and it gets put in different places, even. So this is where x lives for this run of the program, and of course it holds 42. So star p and just x, they're like synonyms, right? I could have just said x. And because ampersand x, the address of x, is held by p, instead of this, I can also just say p. These are the same? These are the same. Interesting, huh? So these are the locations of x, and these are the values held in x, okay? You can get there by saying x or by dereferencing p. Okay, so here we go. Let's continue. So the idea is that when you dereference a pointer, you get the value of the pointee, we say, the thing that it's pointing to. So it goes into memory and gets the contents of the box that's there. So if x was at address 100 again, and p was at address 104, and dun dun dun. Doesn't really matter what x was. Maybe it was like 5 or something. Let's make it what it was before. Yeah, it was still 5. Cool. You can say star p equals 6. And instead of just going to the place, like p is pointing to x, remember, it holds address 100. Instead of just getting the value, you can also set the value. It's essentially equivalent to x. It's equivalent to the line x equals 6. Okay? Because p points to x. So follow the pointer, go to the thing here, change it to 6. That's what it's doing. Okay? This is also something that you can do on both sides. You can use star p. You can say x, it's equivalent to x equals x plus 1. Okay? Because star p, it's just, okay, go to the address, affect the box that's there. It's just saying, all right, this, I'm setting this, and I'm setting it to, well, okay, whatever it is, plus 1. I hope you see that. It is a weird concept to get ingrained in your mind, but slowly but surely, I promise it'll be there. So now it holds 7. If you were to print x or to print star p, you would get back the value 7, because that's what it holds. Here we go. So what do I want to do? Star p equals 6. That changed x, first of all. Now it's 6. And then I can also say star p equals star p plus 1. And again, that's going to go and change x still. Yeah? And so I can print it out as x, of course, or I can print it out as star p. Yeah, same place. They're talking about the same place in memory. That's all. I have two ways to talk about x now. So that is indirection, we say. The power of indirection, the power of dereferencing pointers, the power of having pointers in the first place, I guess. So now, how do we fix this? How do we fix it? Well, here's the answer. We change the variables, the parameter a here, we don't make it just a normal int. We make it a pointer to an int. Okay, you read it backwards. The star you can read as pointer. So we say a is a pointer to an int. Yeah. So if it takes a pointer, it can affect the value that the pointer points to. Yes, yes, yes. And so all we have to do for it to actually alter age is to not pass age itself, but to pass the address of age. Isn't that beautiful? So that means, like, pretend this is all the same again. We're passing along the address of age to birthday, and that means a is going to get set to 100, which is the address of age in main, and then we can dereference a and touch this box. Isn't that beautiful? That's wonderful. That's mind-blowing, right? And here's where I tell you that secretly this is what references are doing for you. References are like an alternative to pointers, where it's a lot harder to mess things up. I haven't shown you how to mess things up yet, but believe me, it's easier to mess pointers up. So let's go and change this so that it actually works. Yes, yes, yes. This is all you have to do. Just say int star a, pass the address of age, and suddenly, because we're working with addresses, we actually have to dereference a, excuse me. Otherwise we would be like messing with the address that a is holding. Otherwise that would be weird. So now it touched age and birthday, and now age is correctly 20. No, sorry, birthday. Yes, look at that. Look at that. Isn't that wonderful? So it was allowed to follow the pointer, touch the value there, and make it 20. That's glorious, isn't it? Isn't it? So that's wonderful. I think you're starting to get it. Pointers, they're just another kind of variable. You need to use the star, of course, to know what to point to, and you have to give the type along as well. So here is like an example of pointers to doubles. Here's double D. And here you can say, I don't know, double star P2 equals the address of D. And then you can see out star P2. You have to have the types match up. P2 is a pointer to a double. Okay, it can only hold double addresses. That's very important. So if you're going to point to a double, you need a double star. That's the idea. Bam. 3.14. Okay. So now, it's time for me to draw a pretty picture, it seems. So I'm going to draw a pointer diagram. So something that looks like this with arrows and boxes. And I want you to show me all the different ways that you could change the original variable. So let's call the original variable x. Okay, so here's x. Maybe right now it holds 5. And here is p. And here is q. And here is r. I will remind myself for posterity. Future Latin. The next time you're teaching this, don't forget pointers to pointers in your example. Because look at what I'm about to do. So let's pretend that x holds address 100, 104, 108. Actually, let's just have random addresses. This is address 100, this is address 150, this is address 200, this is address 250. Because technically these might take up more than 4 bytes on most machines. X is an int, and it holds 4 bytes though. So P is going to point to X, Q is going to point to X, And R is going to point to Q, actually, believe it or not. So here's what happens. P holds the address of X. It's pointing to it. So P holds 100. Q holds the address of X as well because it's pointing to it. So it holds the 100. And what does R hold? You guessed it. It holds the address of Q because it's pointing to Q. It's 150. Isn't that weird? So I want you to tell me all the different ways that you can change X. Like make it 6 or something. Tell me how. And I'm not talking about something like plus plus, X plus plus versus X equals X plus 1. Those are equivalent in my mind. Show me all the different ways you can use the pointers as well as X to change things. Okay? So change X to 6 with a simple assignment. Try it. Okay? And let's see what you come up with. Here are all the ways that you can do it. You can say X equals 6. You can set it like that. You could say star P. You could follow this to get to X. Star P equals 6. Those are the same. Similarly, you could say star Q equals 6. Go to the place that Q is pointing to. Affect the value there. And then this is the tricky one. You can use R, but you gotta do it the right way. If you say star R, that gets you here. Yes? That gets you to Q. Star R gets you to Q. That is not good enough. We want to get all the way to X. But wait, Q points to X. If we just followed Q, we could then change X itself. Double star. Isn't that cool? That is the secret. 2 stars. Okay? Star star R equals 6. What? That's interesting. So, given this diagram now, I'm going to copy it. I want you to tell me what the types of these pointers are. All these variables. So, X is an int. Okay, just remember that for now. Okay. So, we definitely have int X. That's how we declared it. What about these? How was P and Q declared? How was R declared, even? So P, it's pointing to an integer. So we have to say int star. Okay? We have to hold the address of an integer, so we say int star P. Same for Q. It needs to hold the address of an integer, so we have to put the type correctly. It's int star Q. That's how you declare it and make this box. Okay? Now the interesting one is R. R holds the address of something, but that something is itself a pointer, which is very odd to think about, I know. R holds the address of Q, but Q's type is int star. So if I want a pointer to an int star, I have to add a star at the end of that type. I am forced to say int star star R. You see that? R holds addresses of int stars. Weird, huh? It holds pointers to ints. You can read it backwards like that. Isn't that weird? It's very cool though. Let me show you. Dun dun dun. So even further down, we can use int star star R equals the address of P, because P is the only pointer I have so far up here. It's the pointer to X. So R points to P, which itself points to X. You see that? So you can say cout star star R. That's equivalent to cout star star, or cout star P and cout X. It's all talking about X at the end of the day. Follow R to get to P to get to X. It's very weird, but it's useful sometimes. There we go. It is holding 7. Isn't that fun? So that is the beauty of pointers, and now it's my job to tell you the downsides as well. I am sorry. With great power comes great responsibility, right? So this is where I have to talk to you about the responsibility that you have when you're touching addresses, because you can use addresses that don't belong to you. It's unfortunate. So let's talk about segfaults. I've talked to you a little bit about this before, but I want to go in depth now. So first of all, memory costs money. We only have so much of it inside of our computer because there is not infinite space inside of our little tower of a desktop or little rectangle of a laptop. And also, we don't have that much money either, right, to buy 1,000,000 gigabytes of RAM. And first of all, that's true. Second of all, your operating system, like Windows or Mac OS or Linux, it only gives your program so much of that memory. It needs some of it for itself, like to record your screen or something, right? It doesn't give your program all of the memory, which is unfortunate as well, because now you even have less for that program. So if you try to use memory that you don't have, that isn't yours, that would require double the amount of RAM, or if you try to access that special null address, if you try to access null pointer itself, you get what's called the segmentation fault, which we say segfault for short because we're cool like that. And what that is it's a runtime error. I think you've seen that already when you try and access a value or an index into a vector that's way too far out. That is what a segfault is. You're trying to really access memory that's not yours. So let me show you that. So here I am trying to access horrible things. I am sorry. So first of all, let's say int star p equals null pointer. This will segfault because we don't have access, or sorry, it's not going to segfault yet. This is going to hold the null pointer into p, and we don't have access to that. So we shouldn't dereference p. Okay. Watch me do this. I'm sorry. So first of all, let's see out p, and then let's try to dereference the null pointer. This will not be fun. Zero. And oh no, our program got terminated by signal sig_v. Oh no, address boundary error. Oh no. This is what a segfault is. Unfortunate. We can't access address 0. So can't do that. We also can't do this. Oops. Int star q. And then we'll see out q. And also star q. This is wrong for another reason. Actually, this might sometimes work. Most likely will segfault, because q is left undetermined. Oops, segfault, please. It just so happened to hold 0 again, but it didn't have to. It could have held like a really big random number that was an address that we didn't even have inside of our machine. Like, our RAM didn't go that high. That's the idea, okay? That is unfortunate, but the truth. So that is 2 ways to segfault to try and access memory that's not ours, and it's a runtime error because, like, the second we try to do this, nothing makes sense anymore. Like, we're trying to access memory that we can't get. There's no getting around to that, so we have to end the program. C++ just stops the program. Okay? So now, let me show you in these last 2 slides. Let's get through this, and then we'll stop right before this section. Let me show you how to swap things. Okay? Swapping 2 variables is a very important thing to know how to do. So like if you had int x and int y, we would like to swap them to be 43 and 42, right? So the nice way to do it is with references. We already, I think, can make that one work. But let me show you both ways now. Boop. So let's pretend int x equals 42, y equals 43. And now let's swap ref x and y, and I'm going to make the swap ref function. And this uses references, okay? So int reference x, or a maybe, int reference b, and then it's going to swap them. So it needs that temporary variable equals a equals b equals temp. And this should correctly swap the variables because we're passing them by reference here, okay? It's a wonderful thing. Oops, sorry, not segfault, but swapping. Yes, so now x is 43 and y is 42. Quite nice. That's called by reference. Now I want to show you how to do it with pointers. Okay, so we're going to need to use like pointers so that this kind of thing happens. Main, maybe I'll call it swap ptr, and here's a, here's b, here's x, here's y, and a points to x, b points to y, and that'll swap them back because we can follow a and follow b to get to x and y and swap them right back to 42, 43. Okay, so that means, first of all, we gotta swap the, we have to give the addresses, because that's how you make pointers out of variables, right? You gotta get their address. And dun, dun, dun. What I'm about to show you is call by address, or call by pointer, even. You give stars now, and a and b are pointers to ints, okay? So you gotta dereference them. Star A equals star B equals temp. Okay, and this should be called swap pointer. That's all that's different. I want you to definitely look and understand, though, how these are different. They are both going to work. So now we're back to 42, 43. It did swap them. But notice the extra stuff you needed here. You need to dereference things. Okay, A and B had to be new types, pointers, which are slightly different to references, the way we think about them. Okay, so yeah, this is me saying that I think you probably prefer this way. You don't have to use the stars anywhere, but I want you to know how it's really being implemented under the hood. C++ is doing this for you in this function. Okay, secretly. That is references. And now finally, I just want to show you one last thing for this lecture, is the arrow operator. Because we have pointers to classes a lot of the time, okay? So things like strings, those are secretly classes, remember? You can have pointers to strings, right? SP can hold the address of X, and so now SP is pointing to S, which holds A, B, C, D, apparently. That's the idea, okay? You can't use the dot because SP is not itself a string, so this won't work right here. But if you dereference SP to get the string S, then this will work, okay? You can use the dot after you've dereferenced SP, because that will give you the actual string back. But everybody hated this. All the C programmers even hated this because of the precedence rules, of C++ and C. You had to put parentheses around this before you can use the dot. So people thought that was stupid, and they came up with this arrow operator instead. So you can say SP arrow size, and this is equivalent to the dereference and the dot. Okay, SP arrow does both at the same time. It's the combination of those. So let me just paste this into a file for you. Pointers and classes.cpp. Whee. this is the wrong kind of quote. I need to know what a string is, and I think there's, yeah, this won't work, so that's why that's a problem. But these two will, and we can see out them if we wanted to. Okay. And it prints 4. Okay, so that was a lot to just tell you that little piece of syntax. It's new. To dereference and use the dot at the same time, use the arrow. Okay, that's good for your classes that you now know how to make, and the ones that you already know how to use. That's all I got for you. Okay, so that brings us to the end of these slides, or sorry, not these slides, but this lecture, and we will come back and talk about this magical thing called the heap in the next lecture. So, I will see you then.